Today I'm going to show you step by step how you can design, build, and program your own maze following robot. I'm Mr. Pratt and I've been teaching robotics to students for over 10 years. We're going to start by talking about what kind of things you're going to need to do this project, how you actually go about building it, how you go about wiring it using an Arduino board, but it allows you to program it using CircuitPython. Let's go get started. You're going to need a few things for this project. I've got a Metro M4, but an Arduino also fits on top. It's got a half breadboard, and then it's attached to one of these pins that fits well. I'm going to have all these 3D printed files down below. I would suggest you have some sort of alternative servo power delivery. This is what I have set up here. It's got a little UBEC. I've got a video down below. You're going to need a couple different battery mounts. You're going to need a couple rotational servos. This just allows you to take any standard servo and mesh it out to a Technic axle. The last thing you're going to need is a couple battery packs. And of course, the last thing you're going to need is one of your old school EV3 or NXT kits. First thing I'm going to do is I'm going to grab my servo mount here, and I am going to load it up with a bunch of black pins here. The more black pins you put in here, the better, because it makes it less likely for your servo to fall off. Sometimes you can push in the bottom of the table and that helps you fit it in. And then on this one, I'm actually going to run the cable facing forwards, or the cable facing out this way, so that I can mount up on this side of the microcontroller. Now, this is key because our wheel output's actually going to go here eventually. And we need our power output facing away because we're going to put a big brick here. So if you put this barrel jack on this side, you will not be able to plug anything into power. So let's do the same thing on the other side. I'm going to make sure that my points are mirrored. So I'm going to make sure that both of my cables are running backwards here. I'm going to put another 4 pins in. I like to give it a little push on the table just to make sure all my pins are seated. Again, make sure that they are running mirrored to each other. That's looking pretty good. Oh, my board has fallen off. All right, so we're ready to keep going. Now on one side, I'm going to throw in a 3-length axle. And I'm going to put another 3-length axle on the other side. You may find that pushing it on the table helps you get a little bit more force to be able to get those axles all the way in. You also take a small hammer, anything like that would work. Now, next to this, we're going to put on a 24-tooth gear on top of that point. And we're going to run our wheels out the back here. So I'm going to grab 2 6-length axles, run them in on this side to the second last hole. Again, in the second last hole. We're going to throw another 24 tooth on that for both sides. Okay. And then we need some way to make sure this doesn't fall off. So to do that, we're going to use one of these kind of angled brackets and a couple 3-length beams. So I'm going to throw in a cross connector. Actually, on this one, I'm going to do 2 black. Oh no, I need to do 2 3-length beams here. Sorry, not cross connector. 3-length. Run our 3-length hole like so. And then we can mount it on so that it mounts into our frame like that. We'll do the same thing on the other side. I guess technically you don't need a 3-length on the top part. You only need a black hole on the top part. Run our 3-length beam through again. Oh, I built that one backwards. I'll run it through on this side actually. Run it through so that we're not through the center point. Click in, and that should hold our wheel on nice. Now let's get 2 wheels on. The wheel you choose doesn't really matter. I'm going to choose this wheel. Now, before we mount this, we need another 3-length beam, because if we mount this wheel on, you're going to find that it's just going to rub against your surface. Throw the axle connector side on this, the very end, as well as our other point, and throw our 3-length beam on. And then this tire has a shallow side and a deep side. I'm going to throw the shallow side against the robot, because what that allows me to do is now you notice there's just enough clearance that this 3-wheel provides that this wheel is not actually going to scrub against this joint. And now we should have a nice point. You're welcome to put a bushing on this if you think that this might come off. I generally do. Makes life a little easier. We'll repeat the same thing on this side and put in another blue, another black, a 3-length beam. Grab yourself another tire, pop it on, and one more bushing in like so. And that's the first part set up. We've got our wheels ready to rock. The next task for us is to get our battery packs set up. So I'm actually going to mount the batteries inside now. I'm going to take one, slide it through, make sure that the cable runs out this side. I'm going to throw on another couple pins, a couple in the middle here too, just to get us a really nice stable connection. Going to sandwich my other battery pack on top. Then again, make sure that our points line up like so. And then sandwich these two together so I have a nice strong battery box. It's not going to be coming undone on me here. Next thing, I'm going to load up our pins here so that we can connect it to this far side. Now the one thing I want to make sure is that on my design, some of these pins don't actually line up, because sometimes people like to do different designs here. So I'm going to put 1, 2, 3 on this side and 1, 2, 3 on this side. I'm going to skip that middle hole. And then I'm going to line it up so that we mount our point on. Now we need some way of stopping this thing from falling to the ground. So for that, I'm going to use a ball caster. And on this ball caster, I'm going to take one of these 90-degree connectors, push it in like so, push another one up on the top. I've got a little sub-assembly here. I'm going to mount this one in the middle up top so that we've got our joints sliding around, ready to go. Now the last thing we need for a robot is our servo power delivery module. This is going to allow us to get power to our servos. You want to make sure that your power output is on the same side as the outputs for your battery cables. So I'm going to go ahead and throw 4 pins in here. And then slide it in up top like so. Just push mine off. There we go. And then let's wire everything up. So I'm going to grab my 9-volt battery pack, connect that to my servo power delivery board. Grab the 6-volt battery pack, connect that to my Metro board. On my servos, I'm going to route this up through the middle. And then you can choose yourself a servo port. I'm going to make sure that I connect my servo cable to the servo side here, like so. I'm going to choose port 2. And then same thing. Connect it in. And then I need to actually connect my servos. So I'm going to do a common ground on this far side. You can choose any ground port you want on the far side. Let's zoom in a little bit so you can see that. You can choose any ground port, connect it back to your common ground on your Metro controller board. I'm going to choose my common ground back there. And then you can choose any digital pins you want. I'm going to choose digital 0. Actually, sorry, because I have it on 2 and 3, it doesn't really matter, but just for my own sanity, I'm going to choose digital 2 and 3, just so that it's easy, so that I know where my servos line up to. Again, that doesn't actually matter, but it's a little neater for wiring. So with our base Rover assembled, let's get our main sensors on here. You're going to need at least 2 distance sensors. I'm going to use the Electfreak sonar bit. And we're going to attach one on the front of our rover and one on the right-hand side of our rover. So with my battery mounts here, I've got a convenient section where I can just pin these upside down. These are in a little 3D printed mount. I'll leave the STLs up online. Same thing, we'll go ahead and pin this in on the right. Then before wiring up, typically signal pins go to a female DuPont connector. So I've got these little connectors. There's a servo shroud into male jumper pins that make life a lot easier. I'm going to take my right hand side. We'll go ahead and connect it into our servo shroud. Make sure you fully seat these. It's pretty easy to not fully seat these cables, and a lot of people make that mistake. Then I'm going to go ahead and plug into my power and ground on my breadboard. And then I'm going to plug into a digital port. So my right hand side is going to be connected to digital 2. Now before I go further, I'm actually going to go ahead and pull over my ground and voltage to my breadboard. So I'm going to grab off of 5 volts, put it on my power rail here, and I'm also going to grab off of ground. So in my case, ground is green and 5 volts is blue. Now, I'm also going to add 2 little capacitors to this rail. I'm going to add a 0.22 microfarad ceramic capacitor to both lines. It doesn't matter, this can be bidirectional. This is going to help filter out some of that high frequency noise that our sensors might experience. It's going to make them a little bit more reliable. I'm also going to add in a 10 microfarad capacitor here. Capacitors are only one way, so you'll notice on the side of every capacitor I've got this little ground symbol. That's your ground side, or the long lead is your positive side. So make sure you put these in the correct way around. Now with these capacitors, I'm trying to get them as close to my actual main ground rails as I can. And then with the power for my pinning sensor, I'm also trying to get it as close as I can, because the longer your rail is, the more opportunity you have for electrical noise to get into your circuit. Let's go ahead and do the last signal over here. And same thing, I'm going to connect to a digital 3 port and then get nice and close. Now I would suggest you use 5 volt power for these. This distance sensor is 3.3 volts, but in my experience the 5 volt power rail is a little bit less susceptible to electrical noise than the 3 volt rail is. Last thing we're going to do is get my old friend Velcro here, and we're just going to strap everything up so that we don't have these things flying around. Okay, we are wired up, ready to go. Let's go program this thing. First thing we have to do, as always, is start with import statements. We're going to import board as usual, import time, import PWM IO. We're also going to say from sonar bit, import sonar bit, and then from Adafruit underscore motor, import servo. So what are all these libraries doing? Super quick. Board is all of your board-based functions. This is grabbing digital pins. If you don't import board, you can't actually get any pins from your board. Time is, of course, time-based functions, sleep for so many seconds, microseconds, what have you. PWM allows us to create servo objects or pulse width modulation in and out, so we can work with motor objects. The Adafruit motor is a library that allows us to easily control our continuous servos. And then the sonar bit is a library I've made up that allows you to read your distance sensor. You can use an HCS04. I like the sonar bit. I find it's a little bit more accurate. If you need these libraries, I'll include them all in the comments down below. And make sure you have these libraries on the lib folder inside of your CircuitPy device. So inside CircuitPy, if I go to my lib folder, you need to make sure that you have the Adafruit motor and you have the sonarbit.py. I always like to start my code with a pinout. So I'll add in a 3 comments here just for a block comment. And I like to say D0 is the left servo, D1 is my right servo, D2 is my right distance sensor, and D3 is my front distance sensor. This helps remind me where everything is. Now let's take a look at what the algorithm is going to look like. This is the right-hand rule algorithm. So the right-hand rule algorithm should be able to solve any maze as long as a few conditions are true. 1, you have the entrance and the exit on the outside perimeter of your maze. And 2, there are no infinite circle loops at any point within your maze. As long as those 2 conditions are true, this rule will be able to solve any maze. First thing you do is you check the right-hand sensor. If the right-hand sensor detects no wall, you should turn right and move forward 30 centimeters. If the right-hand sensor detects a wall, you should proceed to check the front sensor. Check your front sensor. If it detects no wall, you should move forward. If it detects a wall, you should turn around 180 degrees. So how might that actually work in practice? I've got some really simple mazes here. Let's say we're starting with a robot, and it starts here, and it looks at the right sensor. It detects no wall, so it's going to turn right and face forward. Now we're going this direction. Oh, actually, now you're going this direction. It's going to check the right sensor. It's going to detect a wall. It's going to check the front sensor. Detects no wall, should move forward 1 cube. We're now right here. Check the right sensor, detects a wall. Check the front sensor, no wall, move forward 1 cube. Now here it's going to check on the right. It's going to detect a wall. Check on the front. It's going to detect a wall. It's going to spin around 180 degrees. So now it's facing this way. And now it's going to proceed to check the right sensor, detects no wall. It's going to turn right and then move up and finish the maze. So it seems like at that last point it's a little funny to be doing 180 degrees, but it can do 180 degrees to be able to check its left-hand side in the original condition. Let's go ahead and initialize our hardware. And let's do our servos first. First thing we have to do is create a couple PWM objects. So I'm going to say PWM is equal to PWM IO dot PWM out. And our first servo is at board D0, and it's got a frequency of 50. Pretty common. We can go ahead and copy and paste this over to make a PWM2 object on digital port 1. Now we've created some PWM objects. It's time to actually program these. I'm going to throw in a few more brink lines just so we can work at the top of our board here. Let's actually create our servos. So let's say servo left is equal to servo dot continuous servo with capitals, and this is the PWM object. I'm going to check my pinout. Yes, my left servo is D0. And then I'm going to say servo right is equal to servo dot continuous servo PWM2. So this creates the pulse width modulation object. This actually tells it that it is a servo motor because we could have stepper motors, we could have DC motors. Now we've got our servos set up, it's time to set up our distance sensors. Setting up the distance sensor is pretty easy. We're just going to say distance sensor right is equal to sonar bit with a capital, and then our right is board.d2. And we'll go ahead and copy this up and down, and we're going to have distance sensor front is going to be board.d3. That's all of our hardware initialized. Now to check that our distance sensors are actually functioning, to check that our distance sensors are actually running, let's run a quick while true loop. So we'll say while true, we need to read our 2 distances. I'm going to say distance underscore right for the right one is equal to distance sensor right dot get underscore distance. And then we need to pass in one argument, which is going to be the prev distance right. I forgot to initialize that before. This prev distance right is effectively feeding in the last distance that our distance sensor read. If you want a full tutorial on this, I'll leave a link down on how these sensors work below. But effectively, in order to get our current distance, we pass in the previous distance we read as a bit of an error correction. We'll go ahead and do the same thing. We'll say distance underscore f is equal to distance sensor front dot get underscore distance. And we're going to pass in previous distance f at this point. So I'm also going to have to create a prev distance f function at the top. We initialize it at 570 initially because 570 is the furthest distance that this sensor will be able to read. And then we're simply going to print this. So let's print, we'll say right, comma, distance underscore r, comma again, and then front, comma, distance underscore front. And then when we reset our loop, we need to reset what our previous distances are. So we're going to say prev distance right is equal to the current distance of right, and then prev distance front is equal to the current distance of front. So that when we loop back up, we take whatever the old reading was, feed it into the previous distance, and then we get a new reading. So let's check that these are working as we would expect. So let's go ahead and save this over to our code.py file, open up our serial port, and we should have our right and our fronts. So if I were to take my hand, put it in front of the right hand sensor, we can see that we're pretty close to about 12 centimeters away, which is about what we expect. And if I go and sort of the front, I can see that I'm pretty darn close to being about 9 and in front of it. Let's close up that serial port. We can leave all that code in there because we're actually going to save it for later. And then let's go ahead and actually create our calibrations for our turning. So we're going to need 2 turns. We're going to need a turn right, we're going to need to go forward, we're going to need stop, and we're going to need a U-turn. So let's go ahead and define these functions. So let's define a quick stop function. We're going to go ahead and put in a print stop to help us with some debugging. We'll say servo left dot throttle. It's going to be equal to 0. And then servo right dot throttle. It's going to be equal to 0 as well. And then I'm going to put in a quick time dot sleep for 0.5 seconds inside of this stop. So whenever we call stop, our rover should stop. That should help us with debugging a little bit easier. Let's create our forward function. I'm going to say define forward. I'm going to print forward as a nice little debug. We'll say, and I'm going to copy over the same things I've got from here. And we'll say that our servo left throttle, we'll actually get rid of the time though. Our servo left throttle might be negative 0.5, and our front throttle might be positive 0.5. In order to go forward, because our motors are mirrored with one another, sending one forward, sending one backwards is actually going to make it go forwards. Sending them both the same direction is going to pivot you in place. Now, you're going to have to calibrate this to make sure that forward actually goes forward, because you might find you're going to be drifting. And with a maze robot, you have to make sure these things are pin straight. So let's go ahead and let's go try to calibrate those. So what I'm going to do is inside my while true loop, I'm going to call forward, and then I'm going to call a time.sleep for say 1 second, and then I'm going to call a stop. So all my code's going to do forever is go forward, sleep for a second, then stop. So that's looking pretty good and straight. I'm pretty happy with that. Let's go ahead and make our turns now. So let's define a right. We'll do the same thing. We'll go ahead and copy these up. We're going to print right. And then I'm going to give it a quick time.sleep. And for me, I might say, 0.75, might be 1. Again, we're going to have to calibrate this to make sure we actually get a 90-degree turn. And again, we want to make sure these are both going the same direction. So I'll send them both, and I might send them both at 0.4. Reason I'm not sending them up at fully 1.0 is that you're going to have a little more accuracy if you go a little bit slower. So I would recommend you don't actually do full power for these things. Let's go take a look at this and see if that right is calibrated. Last thing we're going to have to check is do our U-turn. So I'm going to define U-turn so we can turn 180 degrees. And we're going to go ahead and print U-turn. Oops, forgot to put quotation marks in that. And then rather than calibrating something brand new, I'm just simply going to call right. Done. Oh, I forgot a colon there. And that should have us turn around U-turn. Let's check if that assumption is correct. That assumption seems to be correct. With all of our functions set up, we should be able to turn our algorithm into code and actually have this thing solve a maze. So the first thing we need to do is check the right sensor. If the right sensor detects no wall, we should turn right and move forward about a cube. If the right sensor detects a wall, we should proceed to check the front sensor. So we're going to read our distance sensor right. Then we're going to check our right sensor, see if we have a wall. Now my maze is set up in 30 centimeter cubes. So every single 30 centimeters is roughly a maze. So for me, Because of where it is, if I'm reading more than 15, I've likely been in a state where there's no wall in front of me. So we're gonna say if distance underscore r is greater than 15, that means we likely have no wall on the right. And at this point, according to our algorithm, if there's no wall on the right, we should turn right and move forward. So let's turn right, and then let's call forward. Now, because we want to go forward for a bit of time, about 30 centimeter cube, I'm actually go ahead and put in a time.sleep inside of this forward. You might say 1.5. We're gonna have to calibrate this later. But if our distance sensor did find a wall, we'll write an else. We're gonna say likely found a wall on the right. Oops, not in the right, on the right. Now we should go ahead and, according to our algorithm, if we detect a wall, we should proceed to check the front sensor. So now we're going to check the front sensor. If the sensor detects no wall, we should move forward. If it does detect a wall, we should turn 180 degrees. So now, because we've likely found a wall on the right, we should check our front sensor, which we've already done. We're going to say if distance front is greater than 15, that means there's likely no wall in front. We can safely move forward. Else, that means we've likely a wall in front. We're going to call U-turn. So let's go see if this actually solves our maze. So that actually worked pretty well for me. If you find that yours is not solving a maze, you're probably gonna find this isn't gonna work the first time. So my favorite debugging is I turn this off and I look at my robot and I see what should it be doing. Right now it should be reading the right-hand sensor and it should only be saying forward, forward, forward. If I'm over here, I'm starting to get 15 and sometimes even 18. So if I'm here, that means that if this is 18, my code is saying 15, there is still a wall on the right. So I might change my code to say if my distance is greater than 20. And we'll go ahead and put ourselves in this front state here, and we'll see that our front sensor is still reading accurately as we expect. So I hope you found that helpful. If you need some help with debugging, go ahead and put a comment down below and I can help you out with that. And best of luck with building your maze following robot.